Okay, so it's time to look at Bohr's model of the atom. Bohr proposed his model in 1913. He would have been working on it a fair bit before 1913. If you remember, Rutherford proposed his model, made it public in 1911. So 2 years after Rutherford's model came out, Bohr proposes his. Obviously, Bohr would have been influenced by Rutherford's, and actually Bohr bases his model on Rutherford. Now, if you remember, Rutherford's model was like a mini solar system. So the nucleus had positive charge, and the electrons, he suggested, were orbiting around it. But if you remember, Rutherford's model had fatal limitations. One of the limitations was as the electrons orbit around the nucleus, they are accelerated charged particles, and so they would be giving off electromagnetic energy. If they're giving off electromagnetic energy, that would mean they were losing kinetic energy, which would mean they'd be slowing down. And if they're slowing down, now the balance between the force that's pulling them in and the speed that they're going, right, centripetal force, that balance would be broken and they would end up spiraling into the atom. As they give off that electromagnetic energy, we would see it as them giving off continuous spectra of light. So we would see all these little rainbows flashing everywhere. This model, an atom in this model would only be stable for 1/100 millionth of a second. So clearly there are issues with Rutherford's model. So Bohr, realizing that, and Bohr's first name is Niels Bohr, realizing that Rutherford's model had issues, he still thought that some of it was right. So he bases his model on Rutherford's model, but makes some adjustments so that it would be stable longer. Well, I guess anything longer than 1/100 millionth of a second would be a good thing. Now, Bohr also bases his model on the hydrogen atom. Okay, so and his assumption is that if it works for hydrogen, then it'll also work for the bigger molecules. So he bases it on the hydrogen atom, and he offers something like 13 assumptions or propositions. Okay, and so the first one, and some of these are going to sound awfully familiar, some of them are going to sound an awful lot like common sense. So his first one is that electrons orbit in circular orbits around the nucleus. Okay, so just like Rutherford said, circular orbits around the nucleus is his first assumption or proposition. His second one is that he knew that all electromagnetic energy was quantized, so that goes back to Planck. Remember, Planck said there's little packets of energy HF. There's no such thing as a stream in electromagnetic energy. Okay, so there are little packets of energy. Energy is quantized and can only occur in certain amounts. Okay, so little packets of energy that were quantized. So he assumed that all energy was. So we knew this about electromagnetic, so he assumes all energy was, and so that would mean that electrons could only gain and lose energy in fixed amounts. Electrons can only gain and lose energy in fixed amounts. Okay, that's his second assumption. His third one is that electrons could only, and of course he was thinking of hydrogen, but it would be for all of them, electrons could only occupy orbits of fixed energies and no others. Electrons could only occupy orbits of fixed energies and no others. And this is a big difference from Rutherford, right? So Rutherford just said they're orbiting around, but Bohr is saying they're orbiting around, but only of orbits of certain radii. So they couldn't just orbit anywhere. They could only be certain distances from the atom. And his reasoning here is important as to why he thinks his model should be stable, even though Rutherford's wasn't. So he's saying, okay, they can occupy these particular orbits around the nucleus, but not in anywhere in between them. Okay, so that's what he means by they could occupy orbits of fixed energies and no others. It's kind of like you get on an elevator, you can only get off at certain spots. You can't just decide anywhere in the elevator ride that you're going to get off. You have to wait for certain levels, and that's what he's saying about the electrons. There's only certain places, certain distances they can be from the nucleus, and not any others. Okay, his fourth one is that electrons can jump from lower to higher orbits by absorbing a quanta of energy. So electrons can jump from lower to higher orbits by absorbing a quantum of energy. Okay, so if an electron is down here, it can jump up to the second level by absorbing a quantum of energy. If it falls back down to its original level, it will release that exact same quantum of energy. So that's the second part of this assumption. The same amount of energy is released. The same amount of energy is released when the electron falls back down. Falls back down. Okay? His fifth assumption is that each orbit corresponds to a certain amount of energy. So each of these orbits that I've drawn up here corresponds to a certain amount of energy. Each orbit corresponds to a certain amount of energy, with the orbit closest to the nucleus having the lowest energy. With orbit closest to nucleus with the lowest energy. Okay, so the one next to the nucleus would have the lowest energy, and then as you go up, the energy would get higher and higher. Okay? He also said that each orbit was a stationary state, which he called an energy level. So each orbit is a stationary state called an energy level. And I would think you would have heard the phrase energy level from chemistry. Okay? So this is an energy level, this one. So orbits are energy levels. And so then he numbered these energy levels, starting with the lowest one. He numbered them n equals 1, n equals 2, n equals 3, all the way up. So the energy levels are numbered. Starting with the one closest to the nucleus, which would have the lowest energy. Starting with the lowest. And he called that one n equals 1. And these numbers that he gave them are called the principal quantum numbers. Principal quantum number. Okay? So principal quantum numbers, and it's n. Okay, so n equals, so it goes 1 to all the way up. Okay? That's his number 7 assumption. His number 8 assumption is that when an electron, or his assumption or proposal, is that when an electron is in its lowest state, and remember he was doing this for hydrogen, So for hydrogen, it'd be in the